Welcome to the Deep Dive, the place where we transform specialized, often impenetrable technical documentation into actionable, essential knowledge.
Glad to be here.
Today, we are strapping in for a deep dive into something that quite literally underpins the future of one of the world's largest economies.
It really does.
We're talking about India's structural engineering standards.
Indeed. We are tracking a monumental regulatory shift today. And, this isn't just about updating a textbook.
No, not at all.
It's about establishing the blueprint for the next 50 years of Indian infrastructure, from apartment towers to metro systems and, major bridges.
The subject is the leap, the seismic shift, from the venerable IS 456.20.
The Bible for so many engineers.
Absolutely. The reinforced concrete code that has been the industry Bible for 2.5 decades, to the brand new, ambitious, and already controversial draft IS 456.2025, known as the fifth revision.
And this is a really crucial distinction to make right at the start. The IS 456.2000, it's been the standard for a generation of engineers. It saw 6 separate incremental amendments over its life. Fixing typos, adding minor updates here and
It's
there.
just tweaks, really.
Exactly. But the 2025 draft, which was circulated for comments, this is not an incremental fix. It's a complete philosophical overhaul.
A foundational change, you called it.
It's a foundational change from a relatively simple prescriptive handbook to a sophisticated, performance-based structural standard. It's really about aligning India's practices with leading international codes.
Okay, so our mission for you, the listener, is clear. You've handed us the dense comparison documents outlining every single clause change.
A mountain of them.
A mountain, yes. We are going to distill that mountain of technical detail. We need to understand the core technical intent, the massive practical implications for every engineer in the country, and the profound philosophical revolution contained within this 25-year jump.
It really is a revolution.
Because this is about far more than just updating formulas, isn't it?
It is. It's about how complexity is being embraced to achieve, well, unprecedented levels of safety, longevity, and future-proofing.
Okay, let's unpack this immediately. And the story begins with the biggest, most obvious change, which is right there in the name.
Right on the cover.
The old IS 456.2000 had a very specific title: Plain and Reinforced Concrete Code of Practice.
Very clear, very focused.
Simple, focused on concrete cast with rebar. That's it.
But the new draft IS 456.2025, it ditches that historical specificity entirely.
And becomes
It adopts the much broader and more encompassing title, Structural Concrete Code of Practice.
just one word.
That change of just one word, structural, is the first signal of the intention to unify the entire structural concrete ecosystem under one roof.
And the key to that unification, the big structural change, is the full integration of pre-stressed concrete, or PSC.
Yes, that's the big...
Historically, PSC was a whole separate discipline, right?
Yep.
Governed by its own complex, detailed standalone code, IS 1343, specifically the 2012 revision.
Exactly. This is where the scope expansion gets really meaningful. The new draft pulls pre-stressed concrete fully into the general code.
And what happens to the old code?
The proposal is to withdraw IS 1343 entirely upon the 2025 standard's final publication.
Wow.
This systemic shift is, it's incredibly important because modern construction often blurs the lines. Think about precast components.
Okay.
You have elements that are reinforced, some that are pre-stressed, and they all have to come together in these complex composite structures.
So that sounds like a massive headache that designers had to manage before. They were essentially jumping between two different legal frameworks.
2 different books.
Right. Two different books to design one bridge or one large frame.
Precisely. They had 2 separate sets of detailing requirements, often conflicting criteria for serviceability, and different approaches to calculating time-dependent losses.
All of which they had to manually reconcile.
All of which had to be manually reconciled when designing a structure, utilizing both RC and PSC. Unifying them simplifies the load factors, it streamlines detailing, and it standardizes the methodology for analyzing complex members.
So it just recognizes the reality on the ground.
It recognizes that the rigid distinction between basic reinforced concrete and pre-stressed concrete is rapidly becoming artificial in modern infrastructure, where efficiency demands hybrid solutions.
So if we step back from the technical definitions, what does this unification tell us about the fundamental philosophical shift? You said the 2000 edition was very much a prescriptive code.
It was a rule book.
It told you, if your concrete is M30 and your exposure is moderate, you must use X amount of cover and Y water-cement ratio.
Exactly. Do this, get that. The draft 2025 shifts decisively from prescription to performance.
Performance, okay.
It is transforming into a performance-based structural standard. And what that means is the code is less concerned with telling you how to mix your concrete and more concerned with mandating that the final structure must perform measurably against clearly defined, quantified criteria over its entire intended service life.
So the focus moves from checking boxes to actually proving longevity.
Proving it with numbers.
That sounds like a much greater intellectual burden on the engineer, though. You can't just look up a table.
No, you can't.
You have to run a model.
You absolutely do. And this performance focus extends the code's jurisdiction beyond just the design office. The 2000 code was primarily about design and construction rules.
Right.
The 2025 draft formally includes the entire structure's lifecycle: design, construction, and, this is key, maintenance and structural assessment coverage.
Wait, maintenance and assessment coverage, that's huge.
It is.
That means the engineer isn't just signing off on the moment calculations, they are setting the parameters for how the structure should be cared for over the next century.
Exactly. It treats a structure not as a finished product delivered at completion, but as a system with a lifespan that must be managed and verified long after the construction crews leave the site.
So it's a deliberate attempt to combat some of the issues we see with premature deterioration.
It is. It's a direct response to India's well-documented issues with premature deterioration, particularly in harsh climates.
This philosophical move to performance leads directly to the next major shockwave in this draft. The requirements just got significantly tougher.
And much more comprehensive.
The IS 456.2000 operated primarily under just two limit states.
That's right. The limit state of collapse, which focused on ultimate strength and preventing failure.
So will it fall down?
Basically. And the limit state of serviceability, which was concerned with usability, keeping deflection within acceptable limits, controlling cracking, vibration.
A binary safety check, essentially. Is it strong enough and is it usable?
That's it.
The draft IS 456.2025 has blown that up and mandated a new framework, introducing 6 design criteria.
Yes, from 2 to 6.
We are moving from 2 checks to 6. These 6 criteria are strength, serviceability, durability, robustness, integrity, and restorability.
This is a true paradigm shift. It's no longer enough to be strong and serviceable. You must verify and document all 6. Though, the application does vary.
Okay, that sounds overwhelming. Let's break down the necessity. How are these 6 criteria applied in practice? Is every single design, from a small house to a nuclear plant, now subject to all 6?
They are not, which is where the new risk-based governance comes in. The code establishes a baseline. Strength, serviceability, and now durability are deemed compulsory for all concrete designs.
So those 3 are non-negotiable.
Every single structure must satisfy these 3 fundamental requirements. The other 3, robustness, integrity, and restorability, are applied selectively.
And how is that decided?
It's based entirely on the critical nature and risk profile of the specific project, which the designer must formally document in something called the Design Basis Report.
So if I'm building a standard residential complex, I probably just focus on the first 3.
You would.
But if I'm building a major suspension bridge or a subway station, I have to justify the other 3.
Precisely. And this is where the code truly addresses 21st century risks that the 2000 edition simply didn't foresee or codify. And here's where it gets really interesting, diving into those new specialized criteria that fundamentally redefine structural safety beyond just preventing simple static collapse. Let's start with robustness.
Robustness sounds like resiliency, but in engineering terms, what specifically does the code demand?
Robustness is the structure's built-in ability to withstand localized abnormal failure or damage that was not explicitly designed for.
Like an accident.
Exactly.
Yeah.
Think about an accidental event. A large commercial truck impacts a critical ground floor column, or a localized explosion occurs due to a gas leak.
Right.
The structure must manage that initial localized failure without suffering a disproportionate or progressive collapse.
The dreaded domino effect that brings the entire building down.
That's the one.
So it's not enough to say the column can handle its design load. You have to prove the structure has a backup plan if that column is suddenly removed.
Exactly. This requires designers to ensure alternative load paths. The new provisions include explicit checks, often involving the hypothetical removal of a key element, particularly for structures like high-rises, hospitals, bridges, and long-span structures.
This must be drawn from real-world events.
Oh, it's a concept drawn heavily from post-collapse investigations in the UK and US, ensuring redundancy is designed in, not just hoped for.
That's a critical layer of safety. Okay, what about integrity? This seems connected to seismic events.
It is. Integrity requires the structure to transmit inertial forces, the forces induced by rapid acceleration or deceleration, during ground shaking in an earthquake.
Or something else.
Or even during significant sudden foundation settlement, without fracturing or undergoing catastrophic brittle failure.
So it's about holding together.
If you look at seismic collapses, the structure often fails, not because the concrete itself breaks, but because the connections in detailing the structure's integrity cannot hold the pieces together during that dynamic movement.
So it's the difference between a strong wall and a wall that can flex and still remain a single connected unit?
That is a perfect analogy. This criterion mandates rigorous alignment with IS 1893, Part 1, structural categories, ensuring that the detailing, the connections, the confinement of concrete are all sufficient to handle massive dynamic demand.
So it addresses the weak points, the joints.
It addresses that crucial fact that while the column may survive the initial seismic force, if the beam column joint cracks and fails, the integrity of the whole system is lost.
And finally, restorability. This one is fascinating because it implies an economic, not just a structural, criteria.
It does. Restorability, which is required for the most critical and special structures, means designing elements so that if they are damaged in an extreme event, they can be repaired economically and quickly.
Instead of just tearing it all down.
Exactly. Rather than requiring expensive demolition and replacement. This forces engineers to think about repair strategies from day one.
How does that work in practice?
You'd ask, does the design of the connections allow for easy access and replacement? Are the critical structural elements easily inspectable? It's a nod to long-term lifecycle management and minimizing disruption after a disaster.
So, in essence, these three new criteria, robustness, integrity, and restorability, are the code's way of ensuring the structure has a backup plan, uses resilient connections, and has an exit strategy if things go wrong.
Absolutely. And this framework allows the draft to explicitly address high-risk, low-probability scenarios through Clause 6, including blast and impact resistance.
Now, that is a massive shift. The 2000 code was silent on blasts.
Completely. Now, for high-value public buildings, critical industrial facilities, and strategic infrastructure, these loads are design considerations.
What are the engineering demands for blast resistance? It sounds like you need to model high-velocity pressures and shock waves.
You do. The draft specifies 5 key features for blast resistance and shows how integrated the new code is with existing seismic provisions like IS 13920. A blast-resistant structure must have large mass and stiffness to absorb energy, large redundancy, that's robustness, and crucially, members whose strengths are proportioned according to the ductile design provisions laid out in IS 1392.
So the same detailing that helps in an earthquake helps in an explosion.
Precisely. This link is vital. The detailing designed to survive an earthquake, strong connections, and ductile behavior is also the detailing needed to survive an explosion or extreme impact. It's a unified approach to extreme dynamic events.
This shift toward performance and resiliency means the code needs a higher level of oversight. So let's shift from the physics of collapse to the human systems of accountability and design governance.
Yes, the human factor.
The Bureau of Indian Standards didn't just update the equations, they updated the responsibility of the engineer.
They absolutely did. And one of the subtle but profoundly important shifts is the expected expertise of the user.
What do you mean?
The 2000 code was targeted at general practicing engineers. The draft 2025 explicitly raises the bar to competent and experienced engineers.
That doesn't sound subtle.
It isn't just bureaucratic language. It's a necessary prerequisite, reflecting the inherent technical complexity and accountability introduced in this new document.
So if the engineer has to model chloride diffusion rates and check for 6 criteria, you can't have someone fresh out of school just looking up tables anymore.
Precisely. And the core mechanism enforcing this accountability is a mandatory governance requirement, the Design Basis Report, or DBR.
Tell us more about the DBR. Why was formal documentation like this lacking before, and what must it contain now?
Under the 2000 edition, a designer might make an assumption, say, about the structure's intended lifespan or the exact interpretation of an aggressive load condition.
Right.
And these assumptions were often internalized. They were scattered across calculation sheets or maybe vaguely mentioned in tender documents.
So they weren't formalized?
Not at all. The draft 2025 makes the DBR mandatory. This formal document forces the engineer to explicitly articulate and document the entire design philosophy.
Such as?
The targets for service life. Is it 50 years, 100 years? The risk categorization, normal, critical, special. The justification for material selections and the specific performance criteria the design is aiming to meet before the technical analysis even begins.
It's the structural engineer's equivalent of a sworn affidavit, essentially locking in the design intent.
And that transparency is crucial for subsequent maintenance, future assessment, or even a forensic investigation if something goes wrong. And this DBR directly links to that new concept of risk categorization.
Right, the 4 tiers. Explain that again. Normal, important, critical, and special. How does the choice of category impact the designer's workload?
This is instrumental. This categorization determines which of those 3 optional criteria, robustness, integrity, and restorability, must be met.
Okay, so give me an example.
A normal structure, say a small warehouse, only needs strength, serviceability, and durability. Simple. An important structure, perhaps a large office building, might need robustness.
And a critical one.
A critical structure, like a hospital or an airport terminal, may need both robustness and integrity. And a special structure, like a nuclear facility or a defense installation, must likely meet all 6.
So it forces the designer to think critically about the consequence of failure.
Exactly. If the structure fails, how many lives are lost? What is the economic disruption? The higher the risk, the higher the accountability, and the more complex the required analysis.
Moving on to materials, Clause 7 shows India catching up with the reality of high-performance concrete technology.
The materials section is extensively reworked to reflect 25 years of concrete innovation globally. I mean, the old IS 456.2000 generally focused on standard grades up to M40 and high strength up to M60.
Which was a big deal back then.
It was. The 2025 draft expands the upper limit dramatically, including explicit provisions and calculation models for concrete grades up to M100.
M100, that's almost 3 times the strengths of standard commercial concrete.
It is. The draft specifically adds M85, M90, M95, and M100, and here's the real shocker for veteran engineers. M60, which was considered the pinnacle of high-strength concrete in the 2000 edition, is now reclassified as standard concrete under the new framework.
Wow. So what was once high strength is now just normal.
It is. And that simple reclassification tells you exactly how far material technology has progressed in this period.
That reflects the industry's capacity to produce much higher quality, tighter tolerance mixes today. What about steel and the essential ingredients that make concrete sustainable?
For reinforcement, the draft explicitly considers provisions for higher strength steels, moving up to FEF 550, which allows for smaller section sizes and material optimization. But the biggest leap is in the codification of supplementary cementitious materials, or SCMs.
ICMs like fly ash or slag are key to green construction, right?
Absolutely.
Hmm.
The old code had, indirect or vague references to them. The new draft provides explicit recognition and criteria for SCMs like fly ash, both Class F and C variants, granulated blast furnace slag, GGBS, silica fume, and metakaolin.
And why is that so important now?
This SCM codification is vital because it aligns with global sustainability goals by allowing engineers to replace a portion of the high carbon footprint Portland cement with industrial byproducts.
And there's more to it than just being green.
Oh yes. More importantly, using SCMs drastically improves long-term durability, which ties back directly into that mandatory durability criterion we just discussed. It's all connected.
Now we get into the weeds, the core technical engine of the code, starting with flexure or bending design in Clause 9.
Right.
And this is the area that has sparked intense professional debate because the draft moved away from simple, standard assumptions about how concrete behaves when compressed.
It did. In the IS 456.2000, simplicity reigns supreme. For flexure, designers used a single, idealized, parabolic rectangular stress-strain curve for concrete, regardless of the concrete grade up to M60.
One size fits all.
Exactly. And crucially, the strain values were constant, 0.002 at the start of the rectangular block and 0.0035 as the ultimate compressive strain.
That ultimate strain of 0.0035 was an almost sacred number in Indian engineering for decades.
It was. You learned it on day one.
But that constant value implies that M20 concrete and M60 concrete fail at the same strain point, which we know isn't scientifically accurate.
It's not.
So the draft 2025 throws that simplicity out and introduces grade-dependent, strain-based design.
That's the critical technical refinement. The draft acknowledges the reality that high-strength concrete is fundamentally more brittle. It has a lower ultimate strain capacity than lower-grade, more ductile concrete.
And if you don't account for that,
If you keep the same strain limits, you overestimate the ultimate capacity of higher-grade concrete. So that new code requires calculating the peak stress strain and the ultimate strain using straight-line equations based directly on the characteristic strain.
and these are complex linear equations, like the one we saw for ultimate strain, pant 0.003775, 0.00001375.
Yes. They look highly precise, demanding calculation to 5 significant digits. And this push for mathematical precision, a technical achievement designed to align with Eurocode 2 philosophy, is exactly what triggered the professional backlash.
This is the part Dr. Ashok K. Jain referred to as a mathematician's delight but engineer's nightmare. Why is this highly accurate, grade-dependent formula considered a nightmare?
The critique centers on two interconnected, very practical arguments. First is the precision versus reality argument.
What's the point of being that precise?
Why demand 5 significant digits of accuracy, like 0.003500, when concrete is an inherently heterogeneous, variable material? The material strength scatter on site often exceeds the precision gain achieved by the formula. It's rigor for the sake of rigor, divorced from practical tolerances.
So the designer is spending time on complex calculations when the variability of the concrete truck arriving on site is greater than the precision they are calculating.
That's the argument. The second, more damaging critique relates to the practical difference this level of detail makes in the final constructible design.
Okay.
When you compare the calculated moment of resistance using the old constant strain values versus the new 5-digit computed values, the difference for common grades like M40 is often marginal, perhaps 5% to 15%.
Which doesn't sound like a lot.
It's not. In a design office, you don't design a beam for 103 kilonewtons. You group members and size them to 125 kilometers for simplicity and constructability.
So the practical constraints of construction, using standard bar sizes, grouping similar members, making detailing convenient already, swallow up that 5% to 15% theoretical gain in accuracy.
They absolutely do. Dr. Jain's core argument is that such high mathematical precision has no place in RC work. It forces engineers to run complex grade-specific calculations for little practical gain in the overall structural safety margin, considering the primary role of robust detailing and the unavoidable reality of site variability.
So it increases the computational burden without necessarily increasing real-world safety margins.
That's the core of the critique.
That is the perfect tension, the necessary tension we need to explore between academic rigor and construction logistics. Now let's transition to shear design, which is critical because brittle shear failures are always more catastrophic than ductile flexural failures.
Always. And shear design in IS 456.2000 area was widely recognized as the code's weakest point. It was highly empirical.
What does that mean in this context?
It means it relied on semi-empirical shear strength values, the tech table, rooted in experiments from decades ago. Crucially, that empirical approach ignored vital modern parameters, especially the size effect.
The size effect being the phenomenon where, counterintuitively, larger concrete members exhibit lower average shear strength than smaller ones.
Correct. It's a very real phenomenon. The old code also ignored the effect of longitudinal strain, leading to designs that could be unconservative for very large, heavily loaded elements.
So how does the draft 2025 address this?
It adopts a more rationalized, strength-based approach, and yes, it explicitly tackles the size effect.
How does it manifest this correction?
In a couple of key ways. For example, the nominal shear stress allowed for solid slabs is now conservatively capped at half the values provided in the standard shear table.
Why slabs specifically?
This is a direct, practical response to mitigating the risk of brittle punching shear failures, which are common in slabs and often occur suddenly without any warning.
And the draft also encourages advanced analytical tools, like strut and tie modeling.
That's a huge move toward international alignment. The draft explicitly encourages and provides an analytical framework for strut and tie modeling, or STM.
And where is that used?
STM is essential for what we call D regions, or disturbed regions, where standard beam theory, the linear distribution of stress, doesn't apply.
Give me an example of a D region.
Think deep beams, core bells, those short brackets supporting heavy loads, or thick pile caps. These elements rely on complex compression struts and tension ties, and the 2000 code forced designers to rely on highly restrictive, simple rules for these areas. STM provides a clear, mechanics-based alternative.
That said, we've noted that critics suggest the shear provisions don't go far enough to adopt truly modern theories, like MCFT.
That is an accurate assessment. While the draft is a massive improvement, it retains much of the underlying core shear philosophy of the 2000 code.
So it's not a complete rewrite.
It notably does not fully adopt modern mechanics-based theories like the modified compression field theory, MCFT, or variable strut angle models, which are benchmarks in codes like Eurocode 2, ACI, or the Canadian code.
For our listener, can you briefly explain what MCFT allows a modern code to do that the draft 2025 still struggles with?
Well, MCFT provides a sophisticated way to model the behavior of cracked reinforced concrete.
Okay.
It predicts how stress is transferred between the concrete and the steel across cracks, which significantly changes the shear capacity calculation. By not fully adopting MCFT, the draft still relies on empirically derived parameters.
Which means?
It means that for advanced, non-standard designs, especially those involving high shear loads, thin webs, or complex loading designers, may still find that the Indian code requires them to rely on conservative assumptions, and they might still need to supplement their analysis with international code guidance to achieve true, research-based accuracy.
Let's shift back to the macro performance criteria. Durability is now a compulsory design criteria, which is a massive leap forward.
It is.
This marks a fundamental shift from qualitative prescription to quantitative scientific design.
This is arguably the most progressive and economically impactful change in the entire revision. The problem with the durability provisions in IS 456.2000 was their simplicity.
They were just lookup tables.
Exactly. Based on 5 qualitative exposure conditions, mild to extreme, the code specified a fixed nominal cover, minimum cement content, and maximum water cement ratio. If you hit those 3 numbers, you are compliant. End of story.
That seems fine for mild or moderate exposure, but what happens in aggressive environments?
Well, in highly aggressive environments, particularly coastal cities like Mumbai, Chennai, or Kochi, that simple prescriptive cover often proved insufficient.
So the building started to fail.
Within 20 to 30 years, structures would exhibit severe corrosion due to chloride ingress because the prescriptive rule didn't account for the actual mechanism of degradation or the specific concrete mix being used.
So the draft IS 456.2025 moves away from a fixed number to a verifiable lifespan.
Precisely. It introduces the quantitative concept of design service life. The engineer must now formally state the target, say 50 years for a standard residential structure, 75 years for critical industrial facilities, or a much more rigorous 100 years for major infrastructure like metro viaducts or coastal bridges.
So how does the engineer actually prove that 100-year lifespan under the new code rather than just choosing a fixed cover from a table?
They must transition to performance modeling. This forces durability literacy into the core design role.
So it's about the physics of it.
It is. Designers are now required to model the quantitative rate of reinforcement corrosion risk due to external factors, primarily chloride diffusion and carbonation. This is serious physics. They have to calculate the diffusion coefficients based on the specific concrete mix, the types of mineral admixtures, the SEMs we talked about, and the expected local environment.
That means the concrete mix itself becomes a structural design element, not just a commodity you order.
Absolutely. The minimum cover is no longer a fixed number. It is now calculated based on the service life target, the model diffusion rate, and the time it takes for chlorides to reach the level of the steel reinforcement.
So this directly forces the use of better materials in tough environments.
It directly forces the use of high-performance, SCM-rich concrete mixes to achieve a 100-year life in a severe environment. This is paramount for India, which has vast coastal infrastructure and persistent concrete degradation issues.
It transforms durability from a checklist item into a core scientific design requirement.
It does. It connects the lab work of material science directly to the structural design decision. It is a necessary friction point.
Let's shift to the second mandatory serviceability check, cracking and deflection. What updates do we see there?
Serviceability provisions have been rationalized and significantly enhanced. Regarding crack width control, the 2000 code relied on overly simplistic empirical limits. The draft moved away from that and adopts formulations highly similar to those found in Eurocode 2.
And why is the new Eurocode style calculation better?
Because it uses mechanics. Crack width is now calculated as a function of the internal forces, the strain in the steel, the distance from the neutral axis, and geometric factors like bar spacing and bar diameter.
So it's more accurate.
It provides a much more accurate and scientific estimate of the actual crack opening under service loads, allowing designers to precisely control aesthetics, water tightness, and corrosion potential, rather than relying on a gross approximation.
And deflection. Long-term sag, especially in long-span elements, is a frequent problem. How does the draft improve on the prediction of long-term deformation?
The draft provides a significantly improved methodology for calculating long-term deflection, specifically by incorporating detailed creep and shrinkage models.
Creep being the time-dependent deformation of concrete under a sustained load.
Yes, which was often poorly estimated in the past. Now, the calculations rely on determining an effective modulus of elasticity.
And that formula ties the elastic modulus to the creep coefficient.
That's the key. The effective modulus is calculated as EK divided by 1 plus theta, where EK is the short-term modulus and theta is the creep coefficient. The inclusion of that creep coefficient means the engineer must now model the specific time-dependent nature of the concrete mix and the curing conditions to predict the structural behavior 20, 50, or 100 years out.
So if the old method often underestimated long-term sag by 30–50%, this new formula provides a much more realistic estimate.
Exactly. It provides the necessary realism for designing complex structures, like the pre-stressed girders now unified under this code, where managing long-term deformations is absolutely vital for the structure's serviceability and longevity.
Let's discuss the overall analytical structure, starting with Clause 6 on loads. Given the inclusion of blast and seismic integrity, the organization of how a structure is loaded must have been reorganized.
It has been restructured for clarity and sophistication. The draft introduces a vital differentiation between two main categories of actions. First are force loads,
The usual suspects.
the standard inputs engineers are used to: dead load, imposed load, wind load, and the new explicit additions of blast and impact loads. These are direct forces.
In the second category?
They are deformation loads. These include creep, shrinkage, temperature effects, and earthquake shaking, which is ground movement, not a fixed horizontal force.
Why is that distinction so important?
It clarifies that not all actions on a structure are forces in the traditional sense. Some, like temperature change or foundation movement, induce stress through constrained deformation. This is crucial for accurate analysis, especially in highly indeterminate structures.
And how are these applied in verification? The load combinations must also be more sophisticated.
They are. Load combinations are specified in 3 defined sets: basic, accidental, and extreme, each corresponding to a different partial safety factor.
So basic is for everyday use.
Right. Basic covers normal use. Accidental might include a fire or a specific vehicular impact. And the extreme set is for scenarios like a major blast or catastrophic seismic shock.
Which ties back to the 6 design criteria.
Directly. This framework ensures that the designer addresses strength requirements not only under normal use, but also under highly improbable events.
This level of detail suggests that simple 2D frame analysis is no longer sufficient. The analytical sophistication required must have increased dramatically.
Absolutely. Clause 8, structural analysis, explicitly encourages the adoption of linear, nonlinear, and strut and tie methods, moving the profession beyond the historic dominance of simple linear elastic analysis.
It also addresses P-delta effects, right?
Crucially, yes. The draft formally addresses geometric nonlinearity, known as P-delta effects, which is where the deflection of the structure induces secondary moments that amplify the load. And it adopts international metrics for this, like the Stability Index Q from ACI 318.
So it's making sure tall buildings are properly analyzed for stability.
That's the goal. However, even this area draws criticism. The differentiation the code makes between an approximate geometric nonlinear analysis and a detailed analysis is seen by some critics as ambiguous, potentially forcing designers into unnecessary and complex modeling without a clear boundary.
Okay, let's pause now to revisit the practical pain points and criticisms from the consulting engineering community beyond the mathematical complexity of the flexure equations.
Right, the real-world friction.
We need to explore this tension between academic rigor and practical feasibility.
The critique is multifaceted. First, regarding mandated safety margins. The draft has been heavily criticized for, including clauses that appear to be overly cautious, lacking a transparent, rational basis, supported by new, dedicated research.
Can you give us an example?
The most cited example is the change to maximum shear capacity.
Right.
The shear strength of concrete has been significantly reduced by 10% to 20% compared to the 2000 code by applying a higher partial safety factor.
Why is this viewed as controversial? If it's safer, isn't it better?
The argument is that this reduction, while safer, is an overly reactive, maybe even panic-driven move following some past failures, rather than one based on a comprehensive, independent research program dedicated to India's unique material behavior.
So the critics are saying, show us the data.
Exactly. If the code is becoming performance-based, they argue every mandated safety margin change should be backed by transparent, peer-reviewed data, not just an increased factor of safety applied across the board.
And the second point, which you mentioned briefly before, is the inclusion of the older method, the working stress design.
Yes, the inclusion of the working stress design, or WSD method, through what critics call the back door, is labeled as regressive.
Why is it regressive?
The overall spirit of the code, the philosophical drive, is towards performance-based limit state design. WSD is an older, generally more conservative but less material-efficient method. Its inclusion is seen as a concession to engineers reluctant to adopt the complexity of the new methods.
So it potentially undermines the whole point of the revision.
It could, yes. It potentially undermines the foundational philosophy of moving structural concrete design into the 21st century.
Let's talk about the real-world impact on the industry, specifically on the design technology side. When a code changes this drastically, the software platforms must surely scramble to catch up.
The transition demands a massive, costly evolution in engineering software platforms like ETABS, STAAD Pro, and others.
They can't just update a lookup table anymore.
No. They must incorporate the grade-dependent strain equations for flexure, implement the iterative shear modeling, and account for the size effect. But the most significant change is in reporting.
Reporting compliance against all 6 criteria, I assume?
Precisely. The software needs to evolve its reporting functionality to check and confirm compliance against all 6 new design criteria: strength, serviceability, durability, robustness, integrity, and restorability, not just the traditional capacity ratios.
That sounds like a complete re-engineering of the software.
It is a complete re-engineering of the internal algorithms and the user interface, which represents a massive investment for software developers and requires users to learn entirely new workflow interfaces.
And finally, the impact on the professional engineer themselves, the human cost of this transition.
This shift forces a much higher level of professional accountability. The Mandatory Design Basis report places the ultimate onus for every assumption squarely on the licensed engineer.
And they need new skills.
The unification of RC and PSC means that specialized design offices can no longer exist in silos. Engineers must adopt integrated design skills, requiring extensive retraining and durability literacy.
The ability to model chloride diffusion rates and carbonation.
It becomes a core requirement for all structural concrete designers. This is essential for safety and sustainability. But it means older engineers, accustomed to the simplicity of the 2000 code's tables, must rapidly adopt complex scientific modeling techniques.
So, what does this all mean? We've seen that the draft 2025 is a monumental effort. It's an act of convergence, drawing heavily from international standards like Eurocode 2, ACI 318, and the FIB Model Code 2020. It's ambitious.
This is truly the most significant update to Indian concrete standards in 50 years. The intent is clear, it's laudable, and it's necessary to make infrastructure safer, more sustainable, and longer lasting, pushing for 100-year bridges and buildings, combating premature decay, and integrating extreme event resistance.
But there's a trade-off.
The trade-off is a steep increase in mathematical and computational complexity, imposing a high burden of accountability and necessary investment on the practicing consultant.
The critique we highlighted from Dr. Jain suggests this draft, if implemented in its current mathematically rigorous form, might unintentionally force smaller design offices toward bankruptcy.
Yes, due to the required software investment and intellectual complexity.
And it could potentially lead the less scrupulous private sector to simply continue relying on the old, simpler, but technically less safe practices of the 2000 code.
That is the central, practical challenge facing the industry and the regulatory bodies. The Design Committee has provided a framework for technical excellence. The question is whether the regulatory environment and the professional engineering community can uniformly support and enforce the adoption of that complexity across the entire construction ecosystem.
To make sure that complexity becomes a tool for safety, not a barrier to compliance.
Exactly.
So the final challenge for you, the learner, is this. When designing a critical structure that affects millions of lives, is mathematical and analytical complexity a necessary and unavoidable cost of achieving true, quantified safety, durability, and robustness? Or is it, as critics suggest, simply a barrier that complicates delays and increases the cost of practical implementation on the messy reality of the construction site?
And remember that this draft was in wide circulation, subject to intense scrutiny, with comments due in early 2025. This means the process of refinement is ongoing. The professional community's engagement is vital to ensure that the final published standard provides the right balance, the necessary rigor without the crippling complexity, to successfully transition India's structural concrete practices.
It is a work in progress.
It is, and the final result depends on that crucial professional feedback.